Hello, everyone. Welcome back to the Q&A sessions today for GLMs. And it's my pleasure to have a nice panel here that is composed by Cristina Savin. Cristina is a professor of neuroscience and data science at NYU. And then we have Anqi Wu, who is a postdoctoral fellow at the Center for Theoretical Neuroscience at the Zuckerman Mind, Brain, and Behavior Institute, Columbia University. And we have Memming Park, who is in the Department of Neurobiology and Behavior at Stony Brook. So maybe now in reverse order, Memming, would you like to briefly introduce yourself and maybe tell us something about why GLMs are the most important thing in your life? Or maybe not.
I would say cats are more important than GLMs. Thank you for the introduction. Yes, we can tell you how GLMs are important, but first, brief introduction of myself. I'm Memming. I'm very interested in understanding how neural computation is implemented in the brain, and in particular by analyzing neural data coming from different experimental setups. I'm computational, so I don't do experiments myself. And GLM is very important in my life in many ways. Most recently, I used it yesterday. Yesterday, I was trying to figure out the intrinsic structure of sequential or temporal structure in music. And I was telling my student to analyze data using basic GLMs to fit a autoregressive model to predict the next note in the music from the previous notes. So this was not a neuroscience problem, but oftentimes what you can use these models for is you can first fit the model for the task, and then you can try to open that box to see if the principle that your statistical models are using are similar to what the neural computation would be. It would provide you with hypotheses. So that's where I used it most recently. I use it pretty often, but it's not my main tool. I really like it as a baseline. It gives a very good performance across many different problems. But on top of it, I always try to add on top of it, extra, more powerful tools to understand the brain.
Great, thank you so much. Cristina, would you like to introduce yourself briefly and say a few words about GLMs and how they're important for you?
Yes, so I'm Cristina Savin. I'm a assistant professor at NYU. I'm both affiliated with the Department for Neuroscience and the Department for Data Science. What we do really is sort of trying to understand how computation happens at the level of neural circuits, primarily using theory, but more recently we've increasingly focused on the new development of statistical tools for the data analysis part of the question as well. So historically, we haven't used GLMs all that much, but we spent a lot of time using GLMs recently in the context of a new project that we have, where we're trying to understand how neurons in different areas of the brain respond to a monkey, in this case, so animals doing complex naturalistic tasks. So we have a monkey in virtual reality doing the spatial navigation task. So the monkey sees a flashlight that tells it that is going to be reward over there, and it navigates using the joystick and tries to get to the reward. And as the animal is doing this, we're recording activity for a whole bunch of different brain regions. And these are brain regions where we don't really know what the neurons really care about. So we're using GLMs, more generalizations of GLMs, as a first pass to the data to figure out what it is that these neurons actually care about from this many potential task-relevant variables.
Awesome, thank you so much. Anqi, would you like to do a brief introduction of yourself and tell us something about the GLMs for you? Your video is a bit frozen, but I think your voice is coming through.
Oh, can you hear me?
Yes.
Am I moving? Okay, great. So hello, everyone. I'm Anqi Wu. I didn't join this session yesterday, so people might not see me yesterday. So I'm a postdoc researcher at Columbia Zuckerman Institute. My main research is developing machine learning methods to understand the neural data, understand the brain, and also understand animal or human behaviors. So GLM to me is like, as I think, so model fitting first is a very central part of the research I've been working on, but many things, real world things, or like the brain, the neuroactivity, the relationship we want to study is highly nonlinear. Therefore, GLM is very critical. Usually when people talk about model fitting in neuroscience, people talk about GLM because things are highly nonlinear in real world scenario. And as I show in the slides in the tutorial, I'm not only interested in understand the encoding, like how to map the stimulus to neuroactivity, but as well as from the neuroactivity to the behavior. And also, GLM is way more powerful than you think to model many more different problems in neuroscience. So it will be interesting for you guys alone to explore yourself. But I just want to say, like, GLM is really important to study neuroscience problems. So
Great, thank you so much. Oh, you just unfroze. That's awesome. But we heard you. We heard you perfectly. It was just you had a still image for a second. But that's perfect. That's fine. Like, as long as we hear you, that's the most important thing. Okay, so I suggest we start answering some questions. So the first question is by Amireza Farbaksh. And I'm sorry if I butcher your names. This is very hard. Okay, so Amireza's question is, when using GLMs, we typically use gradient descent for optimization, but it's said to be biologically implausible. Why? Also, I have seen Conrad talking about the brain using backpropagation. What algorithm does the brain use during backprop for optimizing parameters at each stage, if not gradient descent? Who would like to give that a shot?
There's some tricky bits there, right? So, I mean, backprop is a form of gradient descent, right? So those are not separate things. So that's an important point to articulate. Whether or not the brain does gradient descent and on which objective, that's a much more expanded question. So there are people who do research on how the brain could approximate something like backprop using local operations. So the reason why you would think that it's not possible for the brain to do something like that is because the computations that you need to do require information that's distributed at the level of a whole bunch of neurons, and neuron A doesn't know what the information that neuron B has, and the other way around. We are working on approximations of backprop that doesn't have this property, where the information is local enough that you can actually use it as a learning signal for each of the neurons. But it's definitely not a solved problem. So this is a current area of research.
Yeah,
I think we will have more discussions in week 3, where we learn about the real neurons' behavior and learning paradigms over there. I just wanted to add on top of this. So the first part of the question was about GLMs and why is GLM learned through gradient descent or other optimization techniques. I mean, one thing to keep in mind is that GLM is not a model of the biological neuron. I think day 3 and today's discussions in the lectures and the tutorials probably made it clear that these are statistical models that capture some relations, but they're not necessarily a proper neuron model, right? And the way that we're fitting them is by fitting the input-output data patterns, not by we're not trying to mimic how the brain is learning in this case. So for us, the best thing to do is to find the best statistical model to capture what's in the data. And that's why the question of is this biologically plausible or not does not matter in our case. But of course, if we were fitting a model of how the brain works in terms of its mechanistic level, then we probably should not or rely less on these principles.
I mean, people have used GLMs as a more mechanistic model. For example, in the early work of Jonathan Pillow in the retina, I think they're sort of like the map between what we use as a statistical characterization of neurons and what the neurons actually do is a little bit tighter. It's still pretty loose, but I think at that point people actually intermingle them a little bit, and maybe that's a point where it makes sense to ask the question. But in general, when we do data analysis, we try to understand the structure of the data and use that structure in a theoretical context to understand how the neurons do the computation. We're not in one step trying to understand how the neurons do the same computation.
Great. Thank you so much for those answers. Okay, the next question is by Abin Krishnan. Abin asked, has the physicist/engineering approach to neuroscience really helped in solving brain disorders? Why is that? So why is it that the neurologists rarely give an ear to computational neurosciences? Or is it that computational neuroscience is more of theory and less of practical application? That's an interesting one.
Memming, this is on you.
Well, unless Anqi wants to take it. Okay.
I'm just currently offline again.
Oh, really?
Oh no, you're just not. There's no
hear you.
video. You're
I'm still frozen.
Yeah, it's on off.
Yeah.
But don't worry about it. We can hear you perfectly, so that's fine.
So computational neuroscience is a big field. I would say there are many different aspects of computational neuroscience. There are more theoretical parts. There are more, more computational modeling parts. Trying to understand the principles of computation in the brain. There are also more engineering type, analysis, trying to help different kinds of patients and have more applications. So there are certainly parts of computational neuroscience that are relevant for clinical applications. I would say, I would give you an example of where I'm coming from. So I am working on one of the projects that I'm working on, and I'm very excited about, is trying to help comatose patients. So as you will learn in a few days, I think in week 2 or 3, there will be dynamic systems lectures. And what I'm trying to use these computational neuroscience models for is to try to help them wake up from certain types of unconsciousness. So trying to perturb their brain and try to understand how electrical stimulations or other kinds of stimulations would perturb their brain and how to get them out of that unconscious or tractor state. So there are certainly people who are working on these problems, and there are many different interfaces between computational neuroscience and more engineering or more clinical applications. So I would say that they're tightly linked in many places. But there are, of course, a lot of people who are just working on theory.
Yeah, I mean, basic research is going to eventually matter for things, but it's not an immediate link to a clinical application most times. I think brain-machine interfaces are the most obvious point of intersection, where the GLMs are sort of like almost used the same way we're using it in the basic research, but with an application in mind.
I believe they heard from Byron Yu yesterday.
Anqi, do you want to add something?
No.
just making sure here. Perfect. Thank you so much. Next question is by Ken. When fitting linear Gaussian regression models, why can we augment the... I should click this before I read. Okay, so why can we augment the design matrix to account for the mean of y by adding a constant 1 to the matrix? Who would like to take that?
Anqi?
Sure. I mean, you can do that. I think there are just multiple ways of doing it. You can either pre-processing that by demean the data, or you add a constant 1 and learn the offset to account for the mean in the data. Actually, I would suggest maybe doing the later in many cases. Well, I don't know. People do both, so it's actually I actually don't. Maybe there's no strong like preference to which one. To me, I did both. I sometimes demean the data, sometimes I add a constant if I'm too lazy to do that. So I don't know. Other people have opinion about this.
I mean, one thing to note is that for maximum likelihood, these are equivalent procedures.
Well, if you have a Gaussian observation model, if you have a Poisson model, you can't demean. So you have to do
within the context of linear Gaussian models, yeah, for maximum likelihood, adding a bias term, having a 1 in the matrix, or demeaning the pre-processing data are all equivalent. They will give you the same result.
Yeah, but Cristina has made a really good point. For Poisson model, people prefer to add a constant to learn the offset instead of demean, right? If you demean the data, you get negative values, which doesn't make sense for Poisson model. So yeah.
Yeah, so putting the bias in the parameters is more natural for the general setting.
I agree.
Awesome, thank you. Okay, the next question is by Matteo Mancini. Matteo asked, how does a linear Gaussian GLM correct for correlation between regressors, and how the covariance term is simplified in the spike-triggered average scenario? So how is it simplified?
Do you want to take this, Anqi?
How does a linear Gaussian GLM correct for correlation? I don't actually quite understand this question. So in the model we have, we actually assume, oh, okay, sorry. An example we gave in the tutorial, we assume independence among regressors, which means we could write the log likelihood as a sum over sorry, I confused that point. So we okay, sorry. So for the linear case, we don't. Okay, I think this is true when we talk about multiple linear Gaussian model, and okay, so I am confused with the correct term. So usually when people deal with multiple linear Gaussian model, people assume Gaussian distributions, and if you have correlation among regressors, you just assume multivariate Gaussian without independence among regressors, right? If you assume independence among regressors, then okay.
Maybe I can take.
Yeah, I confused myself again with the noise thing. Sorry.
So for spike triggered average, I think there are two different formulations. You can just weight the stimulus by the spike count, or you can also correct it, have an additional term of correction of the correlation within the stimulus distribution. Both of them are consistent estimators for the receptive field, meaning if you have infinite data and you fit perfectly, then they will both converge to those correct solutions. The one that has that correction for the correlations, the XX transpose inverse part, that would converge faster. It's more efficient in a sense. But they're both correct formulations. I don't know if that answered the question.
Yeah, I think that there's a follow-up in the chat. Yeah, so the XX transpose inverse thing is the correction.
Yes, that's the correction, and yeah, that will give you a more efficient estimator, yeah, for smaller data. But for infinite data, they do converge. I think the result is well described in Paninsky 2003, the covariance properties of the 3 spike triggered analysis paper.
Yeah.
Awesome, thank you so much. Next, we have a question by Amit that's about L1 versus L2 regularization. When should we use each? Can you give realistic examples of neural data that require one method over the other?
It's tricky, right? Because These are sort of specifying assumptions that we have a priori that come from neuroscience knowledge in a sense, more than anything statistical. There's also sort of like when we don't really have any particularly informative knowledge, for example, in the context of this kind of experiment that I was mentioning at the very beginning, where we just try stuff and do model comparison because we have no idea. Yeah, there are things to try. It's not always perfectly clear what's the correct answer. There's also the combination of the two. So you can do something like an elastic net where you combine the L1 and L2 and let them fight each other out and not worry about it at all. So there are different kinds of solutions.
It's a sort of an art, I would say. with experience, you'll know better. And sometimes you're not satisfied with either, and you'll look for better priors, which I think is coming soon in your Bayesian lecture.
Yeah.
Yeah, I think L2 norm is more conservative. People might turn to choose to use L2 norm at the beginning at least, and you see how the performance is. And unless you have very strong prior knowledge about your model, then you can, which means you assume the relation, like the mapping would be sparse, and then you use L1 norm. For example, if you try to decode the relationship between some neuron and some output behavior, and not all the neurons respond to, not all the neurons fire during this behavior, then you can impose some sparse prior or sparsity over the relationship. Then most of the neurons will not be firing when you learn mapping from the neural activity to the behavior. And this is very common for people who are more from cognitive side. And if you do a lot of fMRI experiments, and this is usually true, because in fMRI, if you try to do decoding from the whole brain fMRI data to human behavior, then usually you will use L1 norm to do the decoding task, because not all the neuron respond to the specific behavior. So
yeah. So there's a follow-up in the chat that I think it's important to mention. So if you have a lot of regressors, another reason why you might want to use an L1 is for interpretability, that you want to sort of attribute blame to a small set of possible causes to the neural responses of this thing, which is the case again in the monkey virtual reality spatial navigation experiment, where we want to sort of isolate relatively small subsets of features that these neurons care about. Whereas not necessarily that we assume that that's the case, but we kind of reinforce it a little bit in the model to get a more interpretable result. Yeah.
Awesome. Thank you very much. Okay, the next question is by Anna Lebedeva. Can we compare models using likelihood when models belong to different classes? If not, how would we compare performance in this case? For example, RL versus GLM.
We can, for reasons that will become apparent when you actually learn about probabilities properly. So basically, all of these coefficients, all these sort of goodness measures that we're getting from the log likelihood and regularized log likelihood and stuff like that, they're actually under the hood probabilities, so they're in the same units. So that means that you can compare them across models if done properly. But it's really hard to explain this without talking about probabilities, which I don't know how to do without you teleporting yourself into time to next week or whenever it is that you're learning about these things.
Well, you can give it a try with sort of basic concepts, I guess. I mean, they know about probabilities. They don't know about the Bayesian formulas.
Yes.
But,
So all of these things tell you what's the probability of your data under your model, right? So they're the same kind of quantities. And the probability might be have the form of a Gaussian or might have a different kind of form, but they're still probabilities. So as long as they're normalized, then you can do the comparison. Memming, you look confused.
I am slightly confused. I tend to avoid comparing these raw likelihoods.
Yeah, this is why I said that they need to be normalized for them to actually be probabilities and for the units to be the same.
Right. Even with the proper normalization. Oftentimes I don't think they're in the same stick, right? If you have Gaussian likelihood versus Poisson likelihood to capture like binary data, I tend to avoid comparing them in terms of the probability. One
I believe in model comparison, Bayesian model comparison rules.
Oh, Bayesian model comparison, I totally agree.
Yeah.
But if it's just a likelihood.
Yeah, well,
especially when it's just a likelihood on the training data set. One thing to be careful, of course, when you're doing model comparison, I think this was not the question, but just a side note, is that if you try to compare these likelihoods across vastly different models, what could happen is that you might have more primers, more flexibility, or some other kind of differences in the fundamental model, like Gaussian and Poisson, that would make your training data set likelihood very different, but the test likelihood might be what is more important for comparing.
Yeah, so you need to do this on the test data, obviously, because we're not completely Bayesian, so the degrees of freedom of the models are not equated, so you need to account for that by cross-validation. Yeah.
Great. That was a nice discussion. Okay. Next question is by Cédric Foucault. Other than brute force cross-validation grid search, are there often used principles for choosing regularization and/or number of features? For example, neurons for decoding stimulus features for encoding. Neurons for decoding or stimulus features for encoding. And specifically in neuroscience, is there examples for that? For example, assumptions of sparse connectivity in the brain or something like that. Sorry, it's a long question.
I'm still parsing. I forgot what the question was.
So essentially, are there
it's fine. So the cross-validation is, again, it's a way of deciding which model is better. So that's after you've made a whole bunch of design decisions about what your model is. The design decisions are where sort of like expert knowledge about neuroscience or domain-specific knowledge comes into play, and that's a little bit of a black art if you're from the outside. Once you have committed to a model and you fit it, and sort of it's a question of just figuring out hyperparameters. At that level, yeah, you at the very, very minimal thing, you can do a sort of a brute force grid search, or you can do something more sophisticated. So actually, the kind of stuff that we do, we typically have some fancy ways of jointly optimizing the parameters and hyperparameters. So you just cast a bigger umbrella, you make everything a big optimization problem, and try to be clever about navigating that space without getting into much trouble. But depending on the details of the model, exactly what you're trying to achieve, how many hyperparameters you have, different kinds of solutions might turn out more practically useful.
Yeah, it really, like, if I can just comment about this, so these aspects of machine learning seem to be a bit of like a dark art that you sort of like have to learn by doing and experimenting a lot and gaining the intuition of what different manipulations do in terms of optimization, in terms of parameter, number of parameters, etc.
Yeah, but even us, that sort of we've been doing this for years. So sort of like if you see a completely new data set you have no experience with, it's going to take you a few iterations of trial and error to get this working on a new data set. It's not like completely, oh, I know how this works. Whatever data you give me, I'm going to sort it out in one go.
Yeah, there is a field in pure machine learning to just try to do hyperparameter optimization to make the hyperparameter search easier. I see meta learning mentioned in the chat, yeah, but also many similar like hyperparameter search network or something proposed to do that. People are interested, you can take a look at that. And also, when you do a lot of Bayesian, as what I've been doing, there are actually some smart way of doing the hyperparameter selection automatically in Bayesian model that you don't need to do the brute force cross-validation yourself. And although you can't really like do gradient descent on some hyperparameters, but you can still try to use some prior to generate these hyperparameter and to fit the model, which is quite magic. Maybe it's too advanced to talk about that here, but people shouldn't be so desperate that you have to always do brute force. But this is irrelevant to neuroscience. This is purely from the modeling perspective. And in the area of neuroscience, I think people could apply some domain knowledge, to add, say, sparse connection to neuroactivity. If you know, like, this region won't be very directly related to the other region, or both spatially or functionally, then yeah, you can eliminate that connection a priori if you want. There is way to add to impose some knowledge to the model a priori in neuroscience. But yeah.
Good points. It's interesting that all three of us are very Bayesian. So let me give you a non-Bayesian comment on this.
Thank you.
So cross-validation itself is it's a very powerful tool, but one of the weaknesses is that your data set, you're chopping your data set into smaller pieces. So, and oftentimes in neuroscience experiments, your animals will not do millions of trials. They would do like 100 trials or something like that. So your data set is sometimes very small, and cross-validation, if you chop it into half, or if you do a nested cross-validation, then you're really limiting your own data sets. So in traditional statistics, has some powerful tools here in that realm. I'm not a big fan because I'm Bayesian, but I'm just letting you know that there are these tools. There are tools for penalizing and using your entire data set to fit it, right? So basically what you were trying to do in cross-validation is to not overfit your parameters. So what you want to do is penalize your model for that exact amount. And there's principled way of doing so called AIC and BIC and these information criteria. The AIC is short for Akaike information criteria and so on. And if you're really limited in this regime, then you might want to go look into those settings. Yeah. And another thing just to mention is all of these approaches, like the cross-validation or the marginal likelihood approach, the more Bayesian approach, and this information criterion type of approach, these may not give these, they might disagree on their optimal parameters, and that's just the fact that they're not supposed to agree anyways. There are no principles to tie these together. They're all different principles, but it's okay.
So can I maybe ask, since you mentioned that, so what do you do in that case? If you want to interpret those parameters in some meaningful way with respect to your neuroscientific question, and different methods essentially give you different answers, and what do you do? How do you interpret that?
Right. I think we're sort of like we're too inclined to directly interpret parameters of models with respect to actual real data stuff. So just the fact that the model fits reasonably well, like that among all the models that you tried, this particular model fits the best to your data doesn't necessarily mean that it captures the two underlying structure of how the neural responses are being generated. So it could be that you're sort of like you're ignoring some important structure there. So the correct model is not even in the space of things that you've tried. So if you force a wrong model to fit the data as well as it can, it will do something, because by construction it has to do that. But it doesn't mean necessarily that the parameters that it comes up with are going to be extraordinarily meaningful with respect to the real world. So I think there's things that you can do with sort of like whether or not you have like non-zero weights with respect to one particular stimulus dimension. So whether or not the neuron cares about that stimulus dimension at all, that's something that you can ask. Whether this particular shape of the filter is exactly what the neuron cares about, they're sort of like, it's going to get complicated because, yeah. Anyways, so some footnotes and grains of thought are required in the interpretation part.
Right.
I'm not coming up with a good example right now.
If I may add a little bit, I mean, these disagreements are usually more prominent if your models are, if your data is very small or your signal to noise ratio is really bad, right? In that case, you're digging in small things. You're trying to find small signatures of your supporting your model from very noisy data. And that's probably why these are good for generating hypotheses that you want to test with experiments in the future or with larger data sets, right? Yeah. So, but if they disagree, that's probably a good signal that it means you don't have enough data, or your hypothesis is too weak, or your data is not supporting your model very well.
Yeah. Yes, more often than not, the best solution is to beg your experimental collaborator to give you more data, which is also the hardest thing to do.
Great, thank you so much. Okay, the next question is by Xiaoxiong Lin, asking, what are the best ways to prove or confirm sparsity of data? Very practical question.
Prove is a very strong notion.
I don't know how to prove anything.
Yeah, statistically speaking, we just have more and more confidence on it, but not prove. Sparsity of data. I guess what they're asking is
sparsity of the model, probably.
Might be. If it's just a data question, you're just maybe reiterating the definition of sparsity might help, right? For us, the sparsity is just number of non-zeros, really, the proportion of non-zeros.
Yeah.
So if you have a million data points, but most of them were zeros, that's a very sparse data set. There's no hard threshold.
Yeah, spike train is sparse.
Depends on the beginning.
I mean, the thing is, yeah, the sparsity of the data is very different from sparsity of the model. Like spike train is sparse, but the model is not necessarily sparse, and vice versa. So I think what he asks is about the sparsity of the model, why we could use L1 penalty to it, and why this L1 penalty makes sense. If the model is not sparse, then if you do L1, you don't really get the good performance. Like usually for me, you can check the performance empirically, right? You have a non-sparse model and sparse model, and you will have different predictive performance on test data, and then you will know, like, okay, then the sparse model makes more sense. I think from us, where we do statistical modeling to it, so we don't have proof to anything. We just, the data tell us what we should trust. That's how I usually work. I mean, if you have theoretical proof, that would be good. But if you don't, then you can only rely on data and rely on what data tell you. Okay. Xiaoxing said that's what he means by sparsity.
You hit the spot here. Perfect. Okay, let's see. We have some more questions here. There's another question by Ken. Whoops, that just got overvoted somehow. Okay, I'll ask a question then by Krasimir. Elon Musk's Neuralink. Feasibility, safety, potential, question mark. Oh, that's an open question. Okay, so what do you think about Elon Musk's Neuralink? Is that actually feasible? Is it safe? Will we actually ever be able to do that safely? And what's the potential for the future?
I have no opinion that I want to voice in public on a recorded video.
Interesting. I mean, I would ask this question back to Elon Musk's Neuralink. Are they using GLMs? If they are using GLMs, yeah.
So this is a question that you should send an email to Flip Sabis, who is a professor at UCSF and who's the scientist in chief at Neuralink. So he's a neuro electrophysiologist that has worked a lot in motor control, and he would be probably very happy to actually answer those questions. Yeah, so I mean, does anyone want to comment on this?
No.
So I actually want to comment briefly on this, because so you can think about the stated goal of Neuralink, whatever you want to think about that, but the fact is that in terms of technology development, this what they call like the sewing machine, right? That inserts the flexible wires at very specific locations of the brain has been like a real feat of technology, and like all like electrophysiologists, researchers hope that this will be publicly available at some point, because that is a real step forward in terms of what you can do technology-wise in terms of recording. So whether ever Neuralink's stated goal will actually be a reality, we will see. Time will tell. But in the meanwhile, I think that's the effort and the funding spent in that research direction has a big potential of really helping the field of neuroscience in the long run. And so to me, this is a positive thing. Despite the fact that it's a private company doing this. But so, all the recording devices that you can buy for your EFIS rig, they're all built by and optimized by companies. So this is in this way no different. Okay, that was a fun question, kind of. Okay, now
people have lots of opinions in the chat that are a lot more informed than ours would be. So feel free to read that.
Well, and this is obviously a question that we can talk about for hours now, and like get into all kinds of philosophical conundrums and things. But I think this might be better over for over a beer than here. Okay, so a question by Karen Netakoven. Are the decoding and encoding functions inverse of each other, or do they bear any relationship at all? Haha.
Good question. Good question.
You can do a decoded by inverting an encoding model. That involves Mr. Bayes again, which we're not supposed to talk about. But they are mathematically related. The way we were using the GLMs, we were sort of like trying to fit directly an encoding model and directly a decoding model for these purposes, so not doing an explicit inversion. Yeah, the explicit inversion involves a prior, and whether or not that prior is easy to estimate, easy to write down, easy to compute with, how do you want to go about it will depend on that.
Great. Thank you very much. Okay. Oh, look, now we're coming to Ken's question. Okay. In today's tutorial, in comparison to the linear Gaussian filter, nonlinear Poisson filter shows higher weights at some time bins in the window. Does that mean the data is highly nonlinear? How can we tell which model interprets the data better when the two models show a similar trend, but only some weights are higher than the others?
Anqi?
So I'm reading the question. Just like a long question. Poisson filter shows higher weights at some time. I don't think one weight is higher than the other means this is a better model, because you might have a very high weight, but which is due to the noise or something. So usually I don't judge a model, or I don't judge models by how high the weight are. I usually if you somehow, okay, for simulated results, for simulated data, where you know the ground truth, then what you should do is compare the weights instead of saying which is higher. Because the higher the weight is, it just means this neuron is more related to the stimulus or related to the behavior. It doesn't mean it's good or not. It just it's higher correlation or not. So usually when I compare models, show a similar trend. I don't really understand what this trend means, but usually when you compare models, you only compare the predicted performance on model on test data. You don't check the weights, compare two weights and see, oh, which one is better.
Can I answer?
Yeah.
So in the intro, we had this one example where of the poorly fitted filter that had really wiggly weights, that you had really big weight values, but it was just because of you were overfitting the noise. So big weights don't necessarily mean anything. That was sort of like a cartoon counterexample that we had in the intro.
Yeah, I think this is where the question is going.
I mean, typically, if you for the same input-output data, if you fit a Gaussian versus Poisson model, they would look similar, but the real question is which model is better, not, is the weight, when the weight is higher or lower, you can't really say if that's your evidence, right? It's really the predictive power of the model after you fit, is it better or not? Yeah.
Great. Okay. Oh, another stochastic and deterministic. So that's a question by Margaret Magnus. Two terms that have been used in the tutorials but not defined or explained are stochastic and deterministic. Can you give a definition of these terms in relation to the topics discussed at Neuromatch Academy up to this point?
Okay. So I think August's answer is perfectly fine. So stochastic means that there's a noisy component that you're not controlling for. Deterministic is that you get the same answer over and over again. So typically when you talk about variables, whether or not you treat the variable as a random variable so that there's uncertainty about what the value is, or you actually think it's a single number that you maybe try to estimate or something, but you're not treating it as a probabilistically, but as a point estimate. Oh, and now I'm introducing the term point estimate, which is a single number. It's very hard not to accidentally use stuff that I'm not supposed to.
Yeah, I mean, go ahead, Anqi.
Oh, I just want to say, like in the tutorial, for example, if we get back to the model fitting on day 3, right? At the beginning, we introduced MSE model. Y is theta multiplied x. Everything is deterministic here. There's no noise. So in this case, Y will be deterministic. And when we get to the MLE, where Y is theta multiplied x plus noise, now we have uncontrolled term noise to generate Y. So in that case, Y will be stochastic because of the noise. So you can think of the output in MSE is deterministic, and output from MLE kind of model, not MLE model, but like the noisy model is more stochastic. Yeah.
Memming, did you want to add something to that, or was it the same point?
I could add a little bit. So this whole stochastic portion, in terms of a Bayesian perspective, which is going to come in week 2 for those of you listening, is not necessarily that the nature of the process, like we're not saying the brain is deterministic or random. What we're really saying here is, as far as in the Bayesian interpretation, our knowledge about that system is incomplete. So we don't know something about that system. So that part can be modeled as random in some sense. So in many of the cases when you're fitting these kind of statistical models, being stochastic does not mean that we believe that the target system is random per se. It's just there's some mismatch between the models. There's some unknown knowledge. There's some issues, possibly with the measurement, which would be a real noise, but not necessarily a deterministic system is being modeled. Yeah.
Awesome. Thank you so much. I hope that clarified things. Okay, question by Marcus. Can you give a mathematical justification for why L1 regularization picks out important parameters?
Important.
Yeah, that is very subjective.
I don't know what important is. the only thing that you can show is sort of like in the cartoons that we are trying to show is that it gives you solutions that are typically more along the axis than the L2. So the solutions tend to zero out some components. What important means? It's not like the ones that, because you're trying to fit the data, well, presumably the ones that you keep non-zero are there because of a reason, but yeah.
Here's how I think about it. I mean, there are many different ways of making your model sparse, but what's common to them is that you want the parameters that are strongly supported by the data to survive, and the ones that are weakly supported by the data to be pruned away. If you have to prune away some of the parameters, right? So in L1 regularization, as you crank up the regularizer, you'll be pruning out more and more, and hopefully the ones that are pruned out first are the ones that are less supported by the data. And most of the time, these weights are the small weights, not necessarily, but they're the smaller weights. And what survives are the big weights that are strongly predictive of the output.
Mm-hmm.
Great. So I think we should take one last question before we wrap it up. Here's sort of like a little bit more of an open-ended question, maybe, by Francesco Sacadura. Is there any biological motivation for the assumption that neural encoding and decoding is linear, apart from simplifying the maths?
So the way neurons communicate, there's a hand-wavy argument that you may or may not believe. I will try to explain what that argument is, and you can choose whether or not to believe it. So the way neurons communicate to each other is by synapses that are kind of linear things. So they're linear processing units. So if you think about how an extra neuron outside of this population gets information about the neurons within this population, you can think about that as a first approximation as a linear filter. So that might be a reason why you might think that decoding of information from one population by neurons in another population might be linear. As I said, you don't necessarily have to believe this, but this is the kind of argument that people have in mind. A lot of it is really mathematical convenience, to be honest. But if you want to go beyond that would be one way to think about it.
In terms of decoding, I would say if you have an arbitrarily powerful decoder, like a universal approximator type decoder, you can sometimes decode too much. I think I mentioned this in the outro. And if the goal of your analysis is to understand, what the neural signals mean in terms of to the brain itself, not to a super powerful machine learning tool, then you want to know sort of the code. I mean, that's a whole part of the analysis, right? You want to understand what the code is of the brain, and in this case, you want to limit your power of your analysis. And the easiest way of doing so, as Cristina was mentioning, is to assume a simple model, such as a linear model. You can go a little bit more complicated. You can use a quadratic model, which people sometimes do. And there are slightly more nonlinear models that are still in the biologically relevant regime. But of course, we don't know exactly what the code is. We don't know exactly how they're being used. But it seems to be a good proxy so far. And so practical terms, it's very useful to do this kind of analysis.
Yeah, it's also sort of a little bit of an Occam's razor kind of thing, that you want to understand the simple structure before you go to any more complicated structure. So that, again, first pass of understanding might be a linear model in terms of interpretability as well.
Great. Thank you so much for all these answers. So we're coming up to the hour, so we should slowly wrap up. For those questions that have not been answered, I encourage you all to please post them in the NeuroStars forum so that you will get an answer to those. And then maybe I can invite all of our panelists to say a few brief last words. Any words of advice or wisdom you would like to give to the students in terms of maybe specific to GLMs or in general? How would we go reverse? Anqi, do you want to start with that?
Oh, yeah, sure. So One thing, congratulations to you guys, is you have already moved a step forward from model fitting to more complex model fitting, and then you are closer to like computational neuroscience and to really analyze the real brain data. So and you will get to know even more complex models in the coming weeks or days or weeks. But for the model fitting part, basically yesterday's tutorial and today's tutorial are like the main workforce people would rely on. So actually, you can start to do some simple neural data encoding or decoding already. If you're an experimentalist, you have some data, and then you can start to do some analysis with GLM. And there are a lot of interesting extensions of GLM. I think Memming has mentioned a couple of them. But still, GLM, the thing we introduced in the tutorial is very basic, and I would encourage people to learn more about all various kind of GLM by searching the literature, which are really interesting and helpful to analyze the real brain data. Yeah, I won't talk too much about this, but yeah, I think GLM to me is a very, very powerful tool, and hopefully by the end of day 4, like knowing the knowledge from day 3 and day 4, now you have a more systematic way of thinking about how to do modeling and how would I fit a model to my data given different property of the data, like which noise I have and which kind of nonlinear function I should use. Yeah, hope you guys learn something from these 2 days model fitting tutorial.
Thank you.
Yeah.
Christina.
Yes, I want to echo Anqi's comments. So I think that although it seems like a lot for digesting in a day or 2, these are really fundamental things, and they're really powerful and really used a lot. So if you understand these things, you're actually making a really big step ahead in terms of actually being able to do a little bit of actual neuroscience. So in terms of data analysis modeling, there's a lot of other sides of computational neuroscience that we're going to learn about later. But in terms of data modeling, this is actually a concentrated, minimal things you need to know in order to start getting stuff done. And everything more complicated is sort of pretty strongly relying on this conceptual basis. So if you get this well, you can go far. Memming.
Yeah. Well, final words. I think Conrad mentioned, if you like GLMs, consider advanced machine learning techniques, promoting work from his group. I would say sometimes when you look at machine learning, which is advancing in super fast, in so many different directions, there are many different fancy things that are very flashy and very attractive. But if I had any wisdom to offer, is don't chase all fancy things simultaneously, and make sure that you have solid basis before you go for fancy things. And in solid basis, I would say GLM is one of the most fundamental things you should try. But of course, more importantly, you should have fun doing science.
I like that as an ending.
Thank you so much, everyone. That was great. I'll see actually all again in a few hours, and then tonight, I guess, in the Americas time zone for the Americas Q&A. Thank you so much for joining us, and see you later.
Bye.